Hello everyone and welcome to physics. So this is our very first chapter and it's all about introducing what physics is. So let me ask you, when you hear the word physics, what is the first thing that pops into your mind? Some of you might think of formulas, maybe gravity and falling objects, or even space and dark holes. So physics can sound like it's just about equations, but really it's the study of the natural world, the rules and patterns that explain how everything around us works. Now think about it. When you drop your phone, ride a bike, or even flip a light switch, physics is happening right there. So in this course, we are going to start building the foundation to understand those everyday experiences step by step. So the main goal of this chapter is to help you understand what physics really is. Now take a second. How would you describe physics in one word or a short phrase? Now, the second goal is to get comfortable with the metric system and some simple math. So, physics uses meters, kilograms, and seconds to describe the world. And knowing these units helps us understand and compare measurements clearly. For example, if I say something is 1.8 meters tall, can you picture that? So that's why learning the metric system is so useful. It's the language of physics. Now here is what we will cover in this chapter. First, the scope of physics. We will see what physics studies and why it is important. Second, the role of measurement and mathematics, how we use numbers and units to describe the world. And third, physics and everyday phenomena, how the concepts we learn connect to things we experience every day. So as we go through each section, I want you to think about examples from your own life, things you have noticed, experiments you have tried, or even just questions you have wondered about. So physics is not just in the textbooks. It's all around us. Now first things first. What is physics? We will be studying it throughout this course. So let's get a clear picture. Physics is the most fundamental of sciences and studies the basic nature of matter and the laws that govern all physical phenomena in the universe. So think about it. Everything around us, from falling apples to stars in the sky, follows these laws. So physics is also very quantitative. It uses mathematics and measurements to test and explain its ideas. So whenever we learn a principle, we can measure it, calculate it, and see if it matches what happens in real life. So another key point, physics combines theory and experiments. So we come up with ideas, test them, refine them, and build a deeper understanding of the universe. And that is exactly what we will start exploring in this course. So before we jump into problem solving in physics, let's take a quick look at the major subfield of physics. This will also useful if you are thinking about higher studies in physics. Mechanics. The first subfield studies the motion of objects under the influence of forces. So it forms the foundation for many other areas in physics. Next, thermodynamics. This subfield studies temperature, heat, and energy. So think about how your coffee cools down or how engines convert fuel into motion. So thermodynamics explains the why and how of energy flow. Next one is electricity and magnetism. So this area studies electric and magnetic forces and electric currents. From powering your phone to generating lightning in storms, electricity and magnetism are everywhere. Next, optics. So it is the study of light. How do lenses focus? Why do rainbows appear? How do cameras capture images? So optics helps us answer all these questions. And next coming up, atomic physics. So it studies the structure and behavior of atoms. So it helps us understand chemical reactions, lasers, and even why matter behaves the way it does. Next one is nuclear physics. So it focuses on the nucleus of the atom. So this is the field behind nuclear energy, radiation, and understanding stellar reactions in the sun. Next one is particle physics. So this area studies subatomic particles, the tiniest building blocks of matter. Think quarks, neutrinos, and the Higgs boson. This is physics at the smallest scales. And the last but not the least, condensed matter physics. So this subfield looks at the properties of matter in solids and liquids. So it's behind technologies like semiconductors, superconductors, and all the materials in your electronics. And throughout this course, we are going to learn some of these subfields. Here, the first four subfields: mechanics, thermodynamics, electricity and magnetism, and optics. They are grouped as classical physics. These are the ones that developed before the 20th century. And the next four subfields: atomic physics, nuclear physics, particle physics, and condensed matter physics. So they are considered as modern physics because they all emerged during the 20th century. And finally, there are interdisciplinary fields like biophysics, geophysics, and astrophysics. So these combines physics with other areas to explore new questions. So as we go through the course, you will see how some of these subfields connects to everyday life, and to some of the examples we will solve in this class. So on a final note, let's try to understand the difference between physics and engineering. So we have learned that physics is the study of the fundamental characteristic of matter and its interactions. So in fact, it's often called the most basic of all sciences because other sciences build upon its principle. Now here's something interesting. People with physics degrees often end up working as engineers in industry. Do you know why? Because the problem solving and analytical skills they develop in physics are directly useful in engineering. So this brings us to the difference between the two fields. Physicists are usually focused on developing a deeper fundamental understanding of how nature works. So they ask why something happens. And engineers, on the other hand, uses that understanding to create practical tools, systems, and technologies. So they ask how we can use this knowledge. But in reality, the boundary is not that sharp. Physicists often work on applied problems, and engineers sometimes push the limits of theory. So a good example is electronics. Physicists discovered how electrons behave, and the engineers used that knowledge to invent transistors and computers. So we can say that physics and engineering are deeply connected. Physics provides the foundation, theory, principle, and the discoveries, and engineering applies that knowledge to solve real world problems and develop new technology. So in short, physics explains the why and engineering shows us how. Now that we have seen how physics provides the foundation and engineering applies it, let's shift to another idea: the role of measurement and mathematics in physics. So measurements are essential because They allow us to test theories. So in physics, it's not enough to just make predictions. We have to be able to measure and check if those predictions match reality. So, in fact, rather than relying on long, complicated explanations, it's often easier and much more convincing to simply make a measurement. So, if a theory predicts a certain outcome, we can measure the result to see if it is correct. So, let me give you an example. Now, imagine two people make different predictions about where a cannonball will land. One says 100 meters away and the other says 200 meters. So, instead of debating endlessly, the simplest way to test it is to fire the cannonball and measure the actual distance from the firing point to the landing point. So that measurement tells us which prediction matches reality. So precise measurement is at the heart of physics. And the same is true in everyday life. Think about it. Whenever you plan or build something, you are making measurements and applying mathematics. For example, if you are figuring out how many bricks are needed to build a wall, you need to know the length and width of the wall and the size of each brick. So only then you can calculate how many bricks will cover the wall. Now I would like you to think about this. What kinds of measurements have you made, either in school labs or in real life, to test a theory, check a prediction, or solve a problem? Next, let's see why mathematics is so important in physics. First, let's take an example. Now, imagine you have a recipe for just one cake. But now you need to bake 5 cakes for a party. So how do you scale up this recipe? So this is where mathematics comes in. It helps us scale quantities logically and consistently. So to make it clearer, let's use symbols. Suppose we let Q1 represent the amount of an ingredient needed for 1 cake, and Q5 represent the amount needed for 5 cakes. Then mathematically we can write the relationship as Q5 equals to 5 times Q1. So that's the power of math. It gives us a simple equation to scale quantities. Now let's apply this to a real recipe. So for 1 cake we need 300 grams of flour, 250 grams of sugar, 250 grams of butter, 4 eggs, 1/4 cup whole milk, and 1 teaspoon vanilla extract. So to make 5 cakes, we can multiply each of these by 5. So for flour, it's 300 grams times 5, which is 1500 grams. And the same scaling applies to sugar, butter, eggs, milk, and vanilla. You can check the answers later. Now here's a question for you. If you are given the recipe for 5 cakes, not just for 1 cake, you have given a recipe for 5 cakes. Now how would you figure out the recipe for just 2 cakes? So you can pause this video and give it a try. Now you have been given the recipe for 5 cakes, right? So here's the challenge. You only want to make 2 cakes. First, let's set it up mathematically. We know Q5, the quantity for 5 cakes, and we want to find Q2, the quantity for 2 cakes. So the unknown here is Q2. So to get there, we first need to scale down. Let's find the amount needed for just 1 cake. That would be Q5 over 5. So once we have the quantity for 1 cake, we can scale it up to 2 cakes by multiplying by 2. So mathematically we can write the equation as Q2 equals 2 times Q5 over 5. Now let's actually try this. For example, the flour amount for 5 cakes is 1500 grams. So using our equation, Q2 equals to 2 times 1500 grams over 5, right? So you will get 600 grams of flour is needed for 2 cakes. And you can apply the same method to find the sugar, butter, eggs, milk, vanilla for 2 cakes. So you see, once you know how to use math to scale recipes up or down, you can confidently adjust quantities to fit your needs. And this is not just about baking. This skill applies to many aspects of everyday life. And in physics, it is exactly how we manage relationships between quantities, scale problems, and make predictions. Now that we understand the role of measurement and mathematics in physics, there's one more basic concept we need to define values correctly, and that is units. So, units of measurements are an essential part of any measurement. Without units, numbers are incomplete. For example, in our cake recipe example, if we just say 300 flour, that doesn't mean much, right? Is it 300 grams, 300 carbs, or 300 pounds? So without units, the measurement has no real meaning. So that's why we always attach a unit to a quantity. So it makes the information clear and universally understood. So today, most of countries use the SI unit system, also called as the metric system. It is the standard way of expressing units. So the most common quantities in physics are length, mass, and time. And the SI unit of length is meters, SI unit of mass is kilogram, and SI unit of time is seconds. So these are called SI units, and they serve as the global standards for science and engineering. And of course, not everyone has always used SI units. Some countries, including the US, often use older English units like cups, pints, gallons, inches, and miles. So this can sometimes cause confusion, especially in international collaboration. But the main advantage of the metric system is its simplicity. It uses standard prefix to represent multiples of 10. Remember the number, multiples of 10, which make conversions within the system very easy. For example, 1000 meter is 1 kilometer or 100 centimeter is 1 meter. No complicated fractions, just powers of 10. And these are the most common prefixes used in the SI system. For example, the prefix kilo means 1000 or 10 to the power 3. So 1 kilogram is 10 to the power 3 grams and 1 kilometer is 10 to the power 3 meters. So think about it. If you drive 5 kilometers, how many meters have you traveled? So it is 5 times 10 to the power 3 meters or 5000 meters. So similarly, the prefix milli means 1000th or 10 to the power minus 3. So 1 millimeter is 10 to the power minus 3 meters. And the same logic applies for all other prefixes like centi, mega, micro, nano. Now, let's do some simple exercises on unit conversions. A baseball has a diameter of 75 millimeters. Now, can you give the diameters in meters and kilometers? First, convert the unit to meters. Now, here the standard unit for measuring length is meters. So, let's first convert millimeters to meters, right? So, 75 millimeters is 75 times 10 to the power minus 3 meters, or it is equal to 0.075 meters. Now we want to convert this number to kilometers. So 10 to the power 3 meter is 1 kilometer. We can use the prefix, right? So therefore 75 times 10 to the power 3 minus 3 meter is equal to 75 times 10 to the power minus 3 times 10 to the power minus 3 kilometer, which gives you 75 times 10 to the power minus 6 kilometer, or we can write it as 0.000075 kilometers, right? So the next one, if you are told that there are 2.54 centimeters in 1 inch, how many centimeters and meters are there in 1 foot or 12 inches? Now try to solve it by yourself first. So you have given 1 inch is 2.54 centimeter and 1 foot is 12 inches. So what is 1 foot in centimeter? So first you can convert 1 foot into inches. So 1 foot is 12 inches, it's already given, right? And then convert that inches into centimeter, because we know that 1 inch is 2.54 centimeter. It's given here. Now here's the tip. Always set up the conversion as a fraction so that the units you don't want cancel out, and the unit that remains at the end is the one you want. For example, in this example, you want the unit in centimeters and you are converting 1 foot to centimeter. So, and first you know that 1 foot is equal to 12 inches, right? So you can write 1 foot is equal to 12 inches as a fraction, so that the FT unit will cancel out, and here only inch unit remains, right? FT cancels out. Now you need to convert inch to centimeter, and you know that 1 inch is 2.54 centimeter. So you can write it as a fraction. 1 inch is 2.54 centimeters. You can write it as a fraction so that the unwanted unit, in this case inches, will cancel out. So you will get the final answer in centimeter units, right? So remember the tip. Set up the conversion as a fraction so that the units you don't want cancel out, and the unit that remains at the end is the one you want, right? Now try the second part. Convert 1 foot into meters. Okay, so you have given 1 foot is 30.5 centimeters. We just found that, and we know that 1 meter is 100 centimeter. So you need to convert 1 foot to meters. You know it in centimeters, convert it into meters. So how do you solve this? First write it as fraction, right? So you know that 1 foot is 30.5 centimeters, right? And you are converting 1 foot into meters, right? So you write this as a fraction so that FT unit cancels out, right? Now the next one is you need to convert centimeters to meters. In that case, you have to write 1 meter equal to 100 centimeter in a fraction like this, so that the unwanted unit centimeter will cancel out. So in this equation, all the unwanted units, feet cancels out, centimeter cancels out, and meter unit remains, right? Remember the tip. Always remember the tip. Set up the conversion as a fraction so that the units you don't want cancel out, and the unit that remains at the end is the one you want. So the final answer, 1 foot is equal to 0.305 meters. You can do one more example. If the rate of flow in an automatic watering system is 2 gallons per hour, how many milliliters per minute is this? Now, let's say you have given 1 gallon is equal to 3.786 liters and 1 liter is, we know that it's 1000 milliliters, and you need to convert gallons per hour into milliliters per minute. So you have to change two units in here, right? Gallons into milliliters and hours into minutes. Now how are you going to do this? First try to solve it by yourself, right? First change the gallon unit to milliliters and then change the hour unit to minute. Okay, now how are we going to do that? So 2 gallons per 1 hour. You can write the question as a fraction. 2 gallons per 1 hour, right? It's gallons per hour. Now let's first change the unit gallons to liters. So we know that 1 gallon is 3.786 liters. So we can write it as 1 gallon is equal to 3.786 liter as a fraction, so that the unit gallon would cancel out and the volume unit we get as liters, right? And now we have to change the liter unit to milliliter. Remember the question asks the unit in milliliter. So we know that 1 liter is 1000 milliliter. So you can write it as a fraction so that the unwanted unit will cancel out. Here the unwanted unit is liters because the question asks the volume in milliliters. So we can write it as a fraction, so the liter unit cancel out and milliliter unit remains, right? Now in the answer we have the volume in milliliter. Now we have to convert hours to minute, and we know that 1 hour is 60 minutes. So we can write that as a fraction so that hour unit cancel out and the answer would be in minute, right? So the answer you are getting is, the unit is milliliters per minute. So it is 126.2 milliliters per minute. So we have to multiply 2 by 3.786 by 1000 and divided by 60 to get the final answer in milliliters per minute. So remember the tip. Okay, what is the tip? Always set up the conversion as a fraction so that the units you don't want cancel out and the unit that remains at the end is the one you want. So with this we are concluding the second section of chapter 2. So remember, measurements are essential not just in physics but in everyday life. So they allow us to test predictions, solve problems and communicate clearly. Also, by using mathematical symbols, we can write relationships between quantities and then perform calculations. Whether it's a scaling recipe, measuring distances or analyzing data in a physical experiment. And lastly, the unit of measurements are just as important. So without units, a number alone is meaningless. So unit allow us to clearly express any measurement, compare values and make sense of the world around us. Next, let's move into the last section of chapter 1. So why are we studying physics? Because physics helps us understand the fundamental nature of reality. So by learning physics concepts, you will gain the tools to explain how things work in everyday life. So this means you will be able to clearly describe and make sense of common events around you. For example, consider a bicycle. Why does it stay upright when moving but falls over when at rest? So this involves a concept called angular momentum, which we will discuss in chapter 8. So interestingly, this same principle applies to systems both very small and very large, from the model of an atom to galaxies in the universe. And learning physics is not just about solving equations. It's fun, practical, and eye opening. So it helps you understand everyday phenomena as well as the wonders of the universe. So let's get ready to dig in. Starting next chapter, we will begin exploring common phenomena around us, discovering why things happen the way they do, and applying the tools of physics to see the world in a whole new way. So that's the end of our first introductory chapter. Now you know that the physics is the most fundamental of all sciences. It helps us understand the basic nature of matter, energy, and their interactions. And some of the major subfields include mechanics, thermodynamics, electricity and magnetism, optics, atomic physics, nuclear physics, condensed matter physics, and particle physics. And precise predictions in physics are tested through careful measurements with well defined units. And mathematics allow us to describe relationships between quantities, manipulate results, and express concepts clearly. So, physics is not just abstract theory, and it helps us understand and explain things we see in everyday life, from why a bicycle stays upright to how light, sound, and energy behave. And that brings us to the end of chapter 1. Now it's time to put your understanding to the test. Go through the practice questions for this chapter. First, try to solve the equations on your own. Think carefully about the concepts, units, and calculations. Once you have given it your best shot, then check the answers to see how well you did and to understand any mistakes. Remember, practicing on your own is the best way to solidify your learning and build confidence as we move forward in this course.